Let's solve this non-homogeneous system of differential equations. We have x prime equals y plus tangent squared t minus 1 and y prime equals negative x plus tangent t. Now before I get started, I always like to write it up in this form. The x prime vector equals matrix A times my x vector plus the non-homogeneous part, which for us will be tangent square t minus 1 and tangent t. And this part I'm gonna just go ahead and call it f. To get started with our problem, we're gonna work on the homogeneous part first, where simply we're gonna ignore this part and we're just gonna work with x prime equals ax. That's what this is. We're gonna ignore these, so all we're gonna have is this part. Therefore x prime equals y prime equals negative x. I'm gonna write this in matrix form. This is my matrix A, and my x vector is this with the components of x and y. I'm gonna use eigenvalue analysis. Therefore, to find our eigenvalues, we're gonna have to find the determinant of matrix A minus lambda times the identity matrix equals 0. That's what we can see here. Our matrix A subtracted the lambda on the diagonal equals 0. This is a determinant, so we're gonna find it by this times this minus this times this. That's what we can see right here, equals to 0. And we're able to determine that lambda squared plus 1 equals 0. Two roots from this, lambda 1 and 2 is plus and minus I, complex conjugate roots. Now we need to determine our eigenvectors. This is the formula that we're gonna be following. Matrix A minus lambda I times x vector equals the 0 vector. Here it is. My matrix subtracted lambda on diagonal times x1, x2, 0, 0. Turn this into equation form. I'm gonna multiply the upper equation by I, and therefore we're able to determine that these two equations are simply multiples of each other. Therefore we can ignore one and work with only one of them. I'm gonna take this one, bring it down, solve for x2, which will be equal to I times x1. Now at this point we need to know that we're gonna have infinitely many solutions for this problem. Therefore we need to simply pick something. So if we pick 1 for x1, then we plug it in and we can determine our x2 to be equal to I. Now from these two we're able to write up our first eigenvector, x1 and x2 right here, 1 and I. Now if you realize that you had conjugate complex roots, which is plus minus I, you could jump from here and simply find your second eigenvector simply by flipping the sign. 1, negative I. And this is our second eigenvector. If you can't remember that you can take this shortcut, simply solve the same process again, just like we did for the first eigenvalue and eigenvector. There it is. Do it again and it'll simply lead you to it. Okay, so my second eigenvector, 1, negative I. Now to write up our solutions for this, I wrote here my eigenvalues again, just so I can see them again better. Lambda 1 and 2 is 0 plus minus I. 0 is my real part and beta will be my imaginary part. Now I'm gonna break up my two eigenvectors that I found into real and imaginary parts. That's what you see here. The real part of my first eigenvector, imaginary part of my first eigenvector, and same thing for my second one. By doing this, I was able to use this formula and simply write up my first solution, plug in alpha, which is 0, beta will be simply 1, there's a 1 next to the I, and the A and the B will be these two. A will be my real part, B will be my imaginary part, these two vectors. Plug them in, and you can actually simplify them a little bit, and this is my final answer for this x1 solution is 1, 0 cosine t minus 0, 1 sine t. The exact same process I'm going to be using for second eigenvector. Here it is what I broke it up into. I'm going to use this formula for it, plug in the corresponding values, my A and B vectors, what I broke out right here, plug in alpha and beta, and after cleaning it up a bit, we can see that we get 1, 0 sine t minus 0, negative 1 cosine t. Now these two, I can write them out separately, x1 and x2. We simply put it, the top line will be 1 times cosine t minus 0 times sine t. That's what you see here. Second line, 0 times cosine t minus 1 times sine t. That's what's right here. And the same process for this one. Now, these are separate, or I can write them up as a phi matrix. Here is in abbreviated form or filled out form. This is useful because our next formula will depend on it. At this point we are done with our homogeneous part, and we need to work on our particular part. Now, here's the formula that we're gonna be working with in order to get our result. So the matrix phi that we just found earlier times u derivative equals f. Now these are matrices, right? So to go from here to here, it's just a simple matrix operation. To find u prime equals the inverse of phi times f. F is, we designated our non-homogeneous part in the beginning of the problem. By the way, we are using the variation of parameters method. Just, I wrote it right here just to mention it. So, the inverse of phi, we know it, we found it. So here it is, we need its inverse. This is a 2 by 2, so it's fairly easy to find its inverse. That will be 1 over cosine squared t plus sine squared t. And in the matrix, cosine t negative sine t, cosine t. Okay, now here's this formula. We remember it from trigonometry. Therefore, this will simply turn into a 1. And the inverse of phi will be simply just this matrix right here. Okay, back to this guy. We need to find u, not u prime. So we're gonna take an integral of both sides of this equation. So the integral of the derivative of u will give me u. And here I'm gonna take an integral from 0 to t of inverse of phi times f. That's what we see here. This turns into 1 over 1. That's what you see here. This one comes here times f. F is this. And dt. Now this is what we need to solve. And if taking an integral of a matrix is kind of confusing at first part, just remember that you do it the same times like other matrix operations, term by term. Okay, so But first, let's clean this up here. We have two matrices multiplying each other. So let's perform that matrix operation. This times this. That's what we're gonna see right here. Let me zoom in a little bit so you guys can see better. There it is. It's simply this times this. Here's my two results. And now we're gonna go through a pretty long simplification and trigonometry based manipulation in order to turn these into a little bit friendlier terms. And I'm not gonna read them out, but I'm gonna show them closely one by one so you guys can see and check if you got stuck somewhere. Here's some more. From here to here to here, then here. Here, there's a bunch of trigonometry-based simplifications. And here's some more. And after all that simplification, we arrive to this. Some terms that finally look like they are friendly enough to be integrated. So, negative cosine t, and on the bottom, sine cubed t over cosine squared t dt. Now we're simply gonna solve this integral on its own, and then we're gonna solve this integral on its own. The first integral of 0 to t of negative cosine t, nothing complicated, right? We can take out the negative in the front. Here it is solved, plug in 0 to t, and we're able to get a negative sine t. Now the second integral, 0 to t of sine cubed t over cosine squared t. Now first I'm going to manipulate this a little bit and then use formulas to solve it. Here it is. I'm not going to read them out one by one. I'm just going to pause the video and hopefully you can read it and verify if you got stuck somewhere. Here's some more. Pretty long integration. And then some more and more and more, and after you feel like you aged about 10 years, you finally get to the end of it, secant t plus cosine t minus 2. And now we can finally write up our u term, our u matrix, which is negative sine t from the first integral and secant t plus cosine t minus 2 from the second integral. Now let's write up our solution for the particular part of the problem, which will be the matrix phi times the u that we have found right here. That's what you can see here. Matrix phi plugged in, matrix u plugged in. Now we're gonna multiply this out and do a lot of simplifications. Use some trigonometry formulas again. And then some more simplification. We finally arrive to a more friendlier form of it. Tangent t minus 2 sine t. And here 2 times 1 minus cosine t. And all there is left to finally conclude this problem, to write up our final solution. The x vector equals our first homogeneous solution that we have found, the phi matrix times our constants c1 and c2 plus the part that represents the particular solution from here plus tangent t minus 2 sine t 2 times 1 minus cosine t. And there it is. Super long problem, but hopefully if you can do it, you rock. And thank you for watching. Please give a like to the video so others can find it as well, and have a great day.